Number 3, we want to find the volume of the area between the curves when we revolve that area around the x-axis. So let's begin by drawing our curves, right? We'll begin by drawing this one. Y is equal to root of x minus 1. So we'll draw our axis, and then we'll just see that this is just a square root function that has been shifted to the right by 1. So now it begins at x is equal to 1. So it begins here and then goes here, and then let's see, it goes like so. Yeah, so our curve looks something like this, right? This is our y is equal to square root of x minus 1. Let's draw our other line. So we have the line y is equal to 0. So it is this line over here. This is our y is equal to 0. And lastly, we have our x is equal to 5. So 1, 2, 3, 4, 5. Yeah. Oops, that is not what I meant to do. Let's just reduce this a little bit. Yeah, so this is our x is equal to 5. All right, so once we have this, we can very clearly see that the area bounded between these curves is this area over here, and we want to revolve it around the x-axis. So we want to revolve it around this axis. So when we revolve it, we are going to have discs, right? These are going to make discs for us. So it's going to look something like, let's see how we can draw this. It's going to look something like this. Like this, and around there, yeah, where the radius is this height over here, and this has an area. So when we revolve it, it is going to look like these kinds of discs. And when we sum up these discs, right, when we sum them up from it's from 1, which is the boundary over here where it begins, to all the way to 5, we are going to have a volume, right? It's kind of going to look like, it's going to look like this kind of shape over here, you know, if this had a volume, right? We're just summing up all these discs. So let us set up our integral. It is the integral. Now we do know the boundaries because it's where it begins. So we do know that the boundary goes from 1 all the way to 5. And then our area is pi r squared, right? We're summing up all these areas. However, we can see that the radius isn't a fixed radius. It gets bigger as we go on, as we advance on the x-axis, and gets smaller as we get closer to 1. So for example, over here I would have a way bigger ring, and over here I would have a way smaller one. Sorry, I meant disk. So because the radius changes, the radius is a function of x. So we're going to say that this is pi times the height goes square root of x minus 1, and all of this squared times dx. Now, thankfully for us, this is very easy because this is just the integral from 1 to 5. I'm going to put the pi outside because it's a constant, times the square root cancels out with the power, so x minus 1. And then when we integrate it, this gives us pi times x squared over 2 minus x, evaluated from 1 to 5. Now all we have to do is plug in our boundaries. And let's see, this is pi times 25 over 2 minus 5, and then minus 1/2, and then minus 1, so plus 1. So this does give us, let's see, 25 over 2 minus 0.5 is 12, minus 5 plus 1. So this does give us, this gives us 8 pi. Yeah. So 8 pi, and then we say it's cubic units because we don't have units over here. So yeah, that is the volume when we take the area between these curves and we revolve it around the x-axis. And all we had to do was realize it that it forms disks, and we're just summing up the area of these disks whose height changes, or actually the radius changes according to the pink function.